Hi, welcome to the Signal Path. In this episode, we're going to do another Patreon request. We're going to take a look at this inexpensive power sensor. This one claims to operate from 100 kilohertz all the way up to 10 gigahertz, and I only paid $85 for it. And on top of that, it claims to operate from minus 60 dBm to plus 30 dBm. That's a 90 dB dynamic range. But as we know, not all dBs are made equal. So we're going to take a look and see how good or bad this actually is. And as a reference, we're going to compare it to something state-of-the-art. We'll compare it to this Roden-Schwarz 3-diode path power sensor that I've reviewed on the channel extensively. This one works from minus 70 dBm to plus 20 dBm all the way up to 40 gigahertz. That's also a 90 dB dynamic range. But it achieves that with a very particular and unique 3-path diode sensor to achieve the best linearity across this entire dynamic range. Not an easy thing to do. There's also this frequency selective one, which I also have reviewed, a phenomenally unique instrument. And this one works from minus 130 dBm to plus 20 dBm. It has some tricks up its sleeves. It has frequency selection with digitization. Very cool instrument indeed. But this one goes all the way to 40, so it's a more fair comparison. So by using this one as a reference, we can see how this one operates. Now this is supposed to also have a battery inside, although it can't really be that large of a battery given its size, and right now it doesn't turn on. So I'm assuming that the battery is completely depleted. It works with a USB-C port, and it does have a connection here for UART if you want to connect it to the computer. So let's turn it on and compare it to this. And then we're going to completely take it apart also and see how it is built, because it is not built using the same technique in here. I doubt that because the 3-path diode requires some totally custom silicon design in the front end. So I went ahead and plugged this into a USB-C port, and I waited for a long time and nothing happened. I just cannot turn it on. So I got one of these power meters so we can plug it in and see if it draws any current at all. And when I plug it in, and you can see that it does indeed draw about half a watt, 100 milliamp or so from 5 volts, and no, I still can't turn it on no matter how much I wait. It may be that the internal battery is damaged and it never reaches the final voltage it needs for this to be able to turn on, and that's why it doesn't work. Not a good sign for this one, but it looks like we're going to have to take it apart to see what the battery looks like and measure the battery voltage first. And removing the batteries in the back does reveal that we do actually have a battery inside, as to be expected. And we can see what kind of numbers we have. Ooh, that does not look good. Something has happened here. This looks like a leak. That's actually quite bad. That's unfortunate. And for fun, let's take a swap of this and see if we can analyze what kind of material this actually is. I'm going to take a Q-tip here and take as much of this as I can. There we go. Let's see if we can analyze this now. And how are we going to analyze the sample? We're going to use the Agilent Resolve, of course. Now, if you haven't seen the video where I talk all about this, I highly recommend it. It is one of my favorite videos I've made on the channel. For now, I'm not going to spoil it too much. We're just going to use it to analyze the compound. Okay, so here's our sample in front of the Raman aperture. And let's do a scan and see if we can identify this material. Okay, we have some results. So a Raman spectrometer returns the presence of two compounds in the Q-tip. The first one is a microcrystalline cellulose. This particular compound is often used in the manufacturing of some cosmetics and many other applications, and it is possible that it is present in this particular brand of Q-tip. In fact, if you scan the Q-tip all by itself, that is the compound the instrument will return. The second one in the list, the ethylene carbonate, is an electrolyte solvent, and it is used in lithium-ion battery manufacturing to improve the conductivity of the electrolyte, which then improves and enhances the performance of the battery itself. And that is indeed what has leaked out of our battery, and it is consistent with what we see. Isn't it extraordinary that we have a device that can scan and within a few seconds tell us exactly what that compound was that we found? Anyway, this now confirms that the battery is most likely dead, so we can go ahead and replace it. Well, I had to take the whole thing apart to get to the battery wires so I could exchange it, and I thought this is a good opportunity to take a look inside and see how this thing actually works. Here's the display module. And this display module does have a ribbon cable in the back, which then ultimately connects to this main board over here, which has all the digital stuff on it. There's a USB-C connection over here and some battery management that charges the battery. I have soldered these new cables in here to go to a new LiPo battery and put some glue in there because those wires were surely going to come off. Now these two wires actually go through two holes here, originally intended for screws. So this battery thing seems to be a bit of an afterthought, at least as far as the chassis is concerned. Now at the heart of this, we have an STM32 microprocessor. Nothing unusual about that. It's used all over the place in all kind of projects, and it can drive the display directly as well as interface to the RF board. It does have ADCs and so on inside, which are required for making this thing work. A ribbon cable goes from here onto the RF board that does everything else, and this is a nice little circuit board on there. It actually says this is version 7, so a lot of revision must have been gone through this. This is actually quite simple in terms of its design, but the ICs that are used in there are interesting. And I thought that this would be another good opportunity to dive into some theory and talk about how this thing is actually put together architecturally, how it differs from some of the other power detectors and what are its limitations, and whether it can even have a chance of meeting the specification it claims it has. So let's dive into this before we actually start using it. And here we are. Let's take a close look at the front-end circuit and see exactly how it works. I want to use this opportunity to do kind of like a design review and see if we can detect all kind of problems that this circuit could have, what are its strengths and limitations, and really also understand the components that are used. I think it would be fun to do that. So first thing, let's look at the claim specification of the power sensor as a whole. It does claim to measure from -60 to +30 dBm. 30 dBm is 1 watt of power. Let's see if we can actually do that. And it does claim that from 0 to -40 dBm, it has good linearity. And here, quote unquote, good linearity means dB in, dB out. In a sense, they're saying that between 0 to -40 dBm, you're going to get a better representation of the reading. It's going to be more accurate. It does say that it does have a resolution of 0.1 dB. Doesn't really mean anything in this case. It just means that the smallest steps is going to increment this 0.1. But it says nothing about the accuracy or the precision of the instrument. It also does claim to work up to 10 gigahertz. Now that's a little bit optimistic, as we will see once we look at the components. But 100 kilohertz to 10 gigahertz is quite wide, especially because 100 kilohertz is quite low in frequency. Dynamic range of 90 dB, which we saw, of course, from the first claim there. And it does say that it does have an attenuation range of 0 to 31.75 dB. That already tells us that the very front-end component is most likely a programmable attenuator. And it does also say that if you want to measure signals greater than 0 dBm, 1 milliwatt, you do want to engage the attenuator. This probably tells us that that's the user's responsibility. So they're pushing that complexity onto the user, because if you don't know what your power is, of course, you don't know when you have hit 0 dBm, which means that you're going to have to play with the front-end attenuation, making sure these components following it are going to be operating in the linear region. And what's following it? Well, it most likely has to be some kind of a power detector that converts the input RF power to some kind of an analog voltage, which can then be used and digitized by the processor so you can see what the power is. So all of this could, in some extent, be actually automated in firmware, but I don't believe that is actually implemented in this case. So you'd have to do that yourself, and that uncertainty in a measurement environment is always a problem. So let's see what happens to the signal. In the front end, we have the type N connector directly connected to the front end attenuator. Notice how there is no DC block, and that's because this attenuator does allow you to DC couple your signal. But the disadvantage here is that if you have 100 volts sitting over here, or 50 volts or 30 volts, you could damage this front-end attenuator depending on what kind of signal you're trying to measure. There is a DC block over here for the later stages, which is required. And we're going to take a close look at the datasheet of these two components and understand how they will interact with each other and see if any of these claims in the datasheet can actually even be accurate. So let's take a look at the front-end attenuator first. Now notice how this analog voltage coming out here, this analog voltage is going to be proportional to the power coming in. So that's how they basically do it. A low-speed ADC is going to be able to make this measurement. So here's the attenuator. Now the attenuator is a solid-state attenuator, of course, made by P-Semi. This is actually an obsolete part. Probably explains why they're able to get it for a very low price. Now the architecture of the attenuator is very similar to a wide range of switchable attenuators. In all of these, you're going to have a pass-through path and an attenuation path that you can switch in and out. And by sizing these appropriately, sometimes binary weighted, sometimes multiples of each other, in that situation you can synthesize a variety of attenuation by just playing with various combinations of these switches. And these switches are of course going to have to come from control circuitry, which is over here. You can set the address of this attenuator so you can have multiple of them. In this case there's only one. And then you can have a digital interface to just control this. This is also how most electromechanical relays are made in spectrum analyzers, for example, which we have taken apart on the channel and have looked at in great detail. And this allows you to get a lot of different attenuations. The disadvantage here in this being a solid state is that it's going to have limitations in linearity, power handling, repeatability, and so on. But the advantage is that it's dirt cheap and it is tiny, of course. So let's really dig into the datasheet of it. The datasheet is, many pages. So we're only going to look at one of them just to get a sense. So this datasheet talks about what happens if you invoke 1 dB steps and what is the accuracy, what kind of bandwidth you're looking at, and frequency range, and so on. So if you look, first of all, this thing is only rated to 6 gigahertz. So the front-end attenuator is not rated to 10, which means that right off the bat, the claim of this working up to 10 gigahertz is suspect because the performance after 6 gigahertz is not well characterized anyway. And if you look over here, especially between the ranges of 13 to 31 dB, you do have some variation of about 1.4 dB maximum between the attenuation steps. Now, a lot of situations, this may not be a problem, but for instrumentation, you would have to calibrate all of this out, which would mean that a proper instrument calibration table across all the frequencies, all the attenuation settings would have to be stored inside the processor. In this case, I don't think they have done that. And as a result, you're going to have quite a bit of uncertainty, several dBs in some cases, on what the actual measurement would be. That would be my guess without having measured it, because I don't think they have those calibrations in there. And there's a lot of other things that you can talk about here. What is nice here that you can see the P1 dB at the input is 32 dBm, and 30 dBm is the minimum. So there's already a problem in here because the input would hit its compression around the maximum value this thing claims to be able to handle. There's another problem which we will see once we look at its actual maximum input rating. Its IP3 is about 53 dBm, which is quite good. This is a good attenuator, usable for a wide range of applications. But when you want to use it for a power sensor, you'd have to be more careful than that. So let's take a look and see some of these plots that the datasheet provides for us. So here's attenuation error as a function of attenuation setting for a few different frequencies. And unsurprisingly, as the frequency goes up, here is 6 gigahertz, you can see that the attenuation error actually grows as a function of attenuation settings. That's why you'd have to have this entire thing characterized per chip and then store it into the memory. The other thing is interesting is the insertion loss. So you can see that there is some insertion loss associated with the attenuator, to be expected, because it does have resistive and capacitive components. They're going to limit the bandwidth for many, many reasons. And at 6 gigahertz, where the rating is, at 85 degrees Celsius, you're around roughly about minus 2.5 or 3 dB of insertion loss. And that's why it's pretty much rated up to here. They're claiming to run it past this point. So you're going to have quite a bit of insertion loss, which means all of this would also have to be characterized, which itself is a function of temperature, which is a whole other problem. So all of that needs to be there, otherwise the measurement you're making is just simply not accurate. And we will see the challenges of that when it comes to actually testing it. Now, the other thing that's important is the absolute maximum rating of this front-end attenuator. So first of all, it's DC coupled, so you have to be careful with that. But if you look at this, they're saying that the absolute maximum power that you can put at the input of this into a 50 ohm is plus 23 dBm. In fact, as you go lower in frequency, the maximum power handling capability of this attenuator gets worse and worse. So at very high frequencies, about 10 gigahertz or so here, you can put about 23 dBm into it. But 23 dBm is far from the actual 1 watt they're claiming. So I wonder if this component would even survive if you were to put 30 dBm into it. And I'm going to try that at the very end of the video because I don't want to destroy it in case it's not going to survive. Other than that, you can see that it has some classic power supply requirements and so on. So now we have a reasonably good idea about the pros and cons of the front-end attenuator, but now we need a power detector. Now what do you want that power detector to do? Well, it's supposed to have an absolutely massive dynamic range in dB, which means that it's going to have to be some kind of a logarithmic detector so that we can measure reasonably in dB linear power in coming out versus voltage coming out. And I think that architecture was pioneered originally by ADI, and this part is in fact also an analog devices component. And here is the internal architecture of it. So there's a lot of details that I can go into, but I'll try to explain it briefly. We do have a chain of amplifiers in the front end. Now think about these amplifiers being cascaded. What happens is that the total small signal gain of this amplifier chain is just a multiplication of all of their gains. So if I have a gain of A in this one, and I have, let's say, 6 stages in a row, the total gain will be A to the power of 6. Now, of course, A to the power of 6 is an absolutely enormous number. And what ends up happening is that these amplifiers, starting from the final stages, begin to hit compression as the input power grows. So they basically saturate one after the other. And once they saturate, they have this knee voltage that represents the saturation. And that curve would look like this. So the input would grow and the output would grow linearly. And at some point, it will basically compress. And at that point, the gain of the amplifier essentially would become 0. Now, it's not going to be a perfect knee like this. Is going to have some characteristic which needs to be modeled. Now it can be shown that you can extract the slope of the input signal in a cascade of these amplifiers by looking at the detector at the output and summing them together. The mathematics of that are a little bit beyond the scope of this particular video. But it suffice to say is that as you increase the input voltage, you're going to use many detectors, each of them connected to the output of all of these amplifiers, and you're going to sum all of them together. And if you write the mathematical relationships of this power that's coming out, this current that comes out, is going to be related to the input power, and all of these are going to run in compression one after the other. Now, there is a lot of challenges with this. First of all, these knee voltages would have to be calibrated. Everything has to be temperature compensated. Offsets need to be removed, and so on and on. A lot of detail goes into making some of this work. But it's interesting to see that by using a bunch of detectors at the output of a set of limiting amplifiers, you can detect the power in a logarithmic fashion, which is pretty cool. And this equation actually is the equation of the slope of the input signal as a function of the knee voltage and a number of gain stages that you have. And you can see the log term actually does appear in there. So it's very cool. So this gives us a voltage output as a function of a power at the input. Now, this thing itself also has quite a bit of variability and quite a bit of uncertainty associated with it. So I've grabbed two plots here, and let's see what these plots say. They're basically the same plot, they're just a different frequency. This is 900 megahertz, and this is at 8 gigahertz. This part is actually rated to about 10 gigahertz. So here's the power input from minus 60 dBm to 10 dBm. And this line that you see is many samples superimposed. The reason they measure many samples and put them on top of each other is to give the user an impression of how statistically variable these chips are. It's the matching between sample to sample. The thicker these lines are and more of them there are wider apart, the more variation there is. And you can see that these lines are much more coupled together, much closer together than they are at 8 gigahertz. So more variation at higher frequencies, which makes sense because we're more sensitive to the parasitics and parasitic variation of the devices. So at very low powers, our output voltage, or I should say maybe the error is more interesting to look at, the error in dB gets very quickly pretty bad. So at minus 60 dBm, this particular component is not very good and accurately telling us what the input power is. And at higher input voltages or powers, it also begins to saturate very quickly. That's because we have so many amplifier stages. At some point, they're all going to be compressed, and you cannot extract any more information. The error in that situation also grows. So in the middle range, right around here is where this thing is best. And that coincidentally seems to overlap very closely to their original claim that between minus 40 dBm and 0 dBm or so, you have the best linearity, which is exactly the range this thing operates best. But even within this, there is an enormous variation here as a function of error. So the error of this is statistically uncorrelated from the error of the attenuator, which means they superimpose statistically on top of each other across many samples. So as you can see right away, this thing is not going to be very accurate as a result of this unless every single thing is precisely calibrated, not to mention the temperature effects, which are going to sit on top of this. Now, if you look at this little circuit diagram here on the left and the right, the implementation, this is the circuit of the evaluation board of this component that ADI provides. And it is one-to-one based on what is actually on that board. So they just basically copied the circuit from the evaluation board, which is not an uncommon technique. That's why ADI or other manufacturers provide these schematics so that you can use it in your circuits. You can see that this 52.3 ohm resistor is this resistor over here. We do have two DC blocks. Those two DC blocks are exactly present here. This 0 ohm resistor is just the fact that these two directly are connected. This resistor is just this resistor, and so on and on. So it's exactly the same. Now, what about this component's maximum allowable input voltage and so on? Well, the absolute maximum rating of this one tells us that the highest voltage or the highest power you can put in is 12 dBm, which means that if I set this to 0 dB attenuation, and I put in a 20 or a 30 dBm input signal like it claims it can handle, I will blow this one up. At least that's based on the absolute maximum rating of it. It may survive up to some point, but it will certainly get damaged over time. And not to mention that this guy itself, if you set it to its maximum attenuation, would not be able to dissipate 1 watt of RF power neither. So this is going to have limitations. But now we know so much about it. So now we should be able to actually go ahead and connect it to an instrument and do some live measurements on it. And here is our measurement setup that we're going to use to characterize the power sensor. I'm going to be using the Roden Shores SMBV 100B synthesizer, which is a fantastic instrument. It has 180 dB of output power control, which is just crazy. And it also puts out more than 1 watt of power at RF, which would be good to really push this towards this upper range. Now the signal coming from that directly goes into a resistive power splitter. This allows us to do a broadband power division, and then at the left and the right side we have our two power sensors to compare. On the left is the Roden Shores NRP, which we're going to use as the ground truth. On the right side we have our power sensor we want to measure. Note how there are no components and no cables between these, so that we're really measuring these two powers as close to the measurement plane as possible. This is a resistive component, completely symmetric, so I can rely on the power being the same on both sides. I have also connected the NRP directly to the synthesizer rather than the power meter. And the reason is because it allows it to track directly with the frequency I set here, and the number shows up. This makes the recording much easier and makes the configuration of this much easier. You can also, of course, always connect it to the Roden-Schwarz NRX, which I've reviewed in a previous video, which will work just fine. So let's go ahead and zoom in here so we can see both of these numbers at the same time and try a couple of measurements. Okay, I think this is the best way to record both of these numbers at the same time. The number at the top is coming from the Roden-Schwarz power sensor. Now that thing has a floor of minus 70 dBm, so therefore we're seeing numbers smaller than that. Now here when I turn this on, it starts with an offset of 2 dB. I'm not sure why that is. It must be some factory setting they've already programmed into it, so I'm going to keep that. The attenuation is set to 0 dB, so we're going directly into the ADI power detector. Frequency I set to 100 megahertz, which is the frequency that's going to come from the synthesizer. Right now the power is turned off, so both of these are measuring their floor essentially. Let's go ahead and turn on the power. I've already calibrated it to show up at minus 60 dBm. And power on. And let's see, there it is. The Roden-Schwarz is reading minus 60 dBm or so, very close, and this is minus 59.3. So there's about 0.7 dB of difference between them, and I know that the Roden-Schwarz one is recently calibrated and very accurate, and this must be the offset that this instrument has at minus 60 dBm, which is not too bad, considering that we're talking about an $85 unit. Let's go ahead and increase the power by 10 dB. Here we go. So at minus 50 dBm, this is measuring minus 51.1. So it's about 1.1 dB off. Here is minus 40. Minus 40.6, getting a little bit better. Minus 30 is getting closer and closer. And this is the sweet spot of the ADI power detector. We know this because we looked at its data sheet, and indeed that's the sweet spot for it. Here we go, minus 20, we're minus 20.4, perfect. Minus 10, minus 10.2, getting really close. And here is 0 dBm. Now 0 dBm, we're beginning to compress and see issues with the ADI part. It's already measuring minus 1.4, so it's already 1.4 dB off. Now if I increase that, let's say go to 5 dBm, you can see that at 5 dBm we're basically clipped to about 0. So the ADI part can no longer measure. Unfortunately, there's no warning at all in here that you've compressed this device. And without adding the attenuation and checking by moving the attenuation up and down, you have no way of knowing that that compression is happening. This could have been avoided if they had written some more clever firmware in there. Let's go ahead and add 10 dB of attenuation. So with 10 dB of attenuation, the power immediately drops to minus 5. They should actually calculate that ahead of time, but now we have to add these two numbers together. So at plus 10, minus 5, we're measuring minus 4.6. So it's pretty close to the 4.9 that we are supposed to be measuring. Not too bad. Let me go ahead and increase that by 1, so we're sitting at 5. There it is, minus 5.3. That's actually quite close. Now we can keep increasing that also. Here's 10 dB. You see minus 1.4 again. So once again, we're compressing. So it's not very reliable for measuring anything above 0 dBm. Now we can keep increasing this and do this exercise again and go to 15 dBm. Yep, fully compressed again. We need to add another dB of attenuation. Here's 20 dB of attenuation. We get the number back again. So it's reasonable. It's working as long as you keep that in mind. And we can repeat this exercise now at 6 gigahertz. Again, I'm doing the same thing. Power is supposed to be at minus 60 dBm. Let's go ahead and enable that. And what are we measuring? So here is minus 60 dBm from Roden-Schwarz, and we're seeing minus 58.4. Attenuation is 0, and the frequency is 6 gigahertz. So we're a little bit off again. And this distance is going to grow at higher frequencies, as we saw and predicted from the difficulty of operating these devices at higher frequencies. So let's go ahead by 10 dB. Here we go. Minus 50 is reading minus 52.2. Let's go 20 dB higher. So here's minus 30. It's reading minus 31.4. Okay. And he should be here around, let's adjust this to get to about minus 20. And what do we have? At minus 20, minus 21.2. Okay, so it's roughly the same where it was. And here is minus 10 roughly, minus 10.6. And let's get this thing to 0. Here's 0 dBm, minus 1.4. So we're compressing just like before. We're going to need to add some additional attenuation there. Let's take this to, let's say 5 dB, and then add a 10 dB attenuation. There you go, minus 6.2, minus 5.5, yeah, about a dB off or so. So not too bad. It is roughly tracking. It looks like the calibration table may be a little bit better than I originally thought, but it is reasonable again for something that is supposed to be $85. Now, in order to verify the claimed upper frequency range of this at 10 gigahertz, I have to change the setup a little bit because the Roden Shores synthesizer is a 6 gigahertz synthesizer. We need a different one. So we're going to use the Agilent MXG here, which goes to 20 gigahertz in this case, and then we'll combine that with the Roden Shores NRX to interflex to the actual power sensor here. Basically, exactly the same setup in terms of the power distribution, just slightly different equipment. So here's an attempt to measure a minus 10 dBm signal at 8 gigahertz. You can see we are setting this to 8 gigahertz, we're measuring minus 10 dBm, but over here we're set to 8 gigahertz, we're measuring minus 16.6. So it's basically completely gone, it's falling off the edge of a cliff. We can increase the frequency here to, let's say, 9 gigahertz, and at 9 gigahertz we're already at minus 24. So basically it doesn't work at all. So the claim that this is a 10 gigahertz part is certainly false. I wouldn't really use this above 6 gigahertz anyway because it certainly doesn't have the frequency response to cover that. So if you take the temperature, variation, frequency, and everything into account, plus or minus 1.5, plus or minus 2 dB, maybe you can count on this, given that you also don't know the attenuation settings ahead of time. Of course, you'd have to play around with that to find the appropriate setting. You could use this for $85. It's not terrible. Now, it has no input protection, so I do want to try and stressing it, see if it really can take the power it claims to. At least the parts don't seem to be able to. And I do really want to thank my Patreon supporters to make all of this possible. There's also a link in the description. You can support the channel via PayPal if you want. Multiple ways to give back to the community. I don't charge all of my videos to Patreon. Only rarely do I ever do that if the video is extensive and includes a lot of details and analysis and so on. So nonetheless, let's go ahead and now connect this to the Roden Shores where we can put a lot of power into it and see if it survives. So I have set the attenuation to minus 30 dBm. So the P-semi part in the front is going to absorb essentially almost all the power before the ADI power detector. Now we're at 0 dBm. I'm going to enable that. Now keep in mind we're sitting at 500 megahertz, and that does matter as we saw from the plots. And you can see it is measuring correctly. 30 dB attenuation, 0 dBm minus 30.5. So let's increase the power to 10 dBm. And indeed it went up by 10 dB, pretty good. Let's go to 20 dBm. And here it is minus 10. And let's go to 25, minus 5.4, still surviving, and 27 dBm, minus 3.5. So the front end is now compressing as we saw earlier, but 27 dBm is half a watt of RF power. It's a little bit less because of the cable, but nonetheless, it's pretty close. So it looks like it is surviving. Let's give it a few seconds to see if it changes. Still looks good. Okay, I'm going to disable the power. I'm going to apply it again. Goes back to roughly where it was. That's pretty good. Okay, let's back it off all the way back to 0. Let's see if it goes back to what it used to display. Minus 30.5. Yeah, well, that P-semi certainly took that power without any issues. Now let's change the frequency because at lower frequencies, it's harder for that part. Now let's try the same thing at 1 megahertz. I have set everything exactly the same way. 30 dB attenuation is still in place. 0 dBm coming in. 30 dB of attenuation. Okay, it's roughly correct where it should be. Let's go to 10 dBm. All right, still looks good. 20 dBm, minus 10 looks good, and 27. There we go. It's fully compressed, of course. We know this. It doesn't work well here, but at 27 dBm, it's reading 0. Okay, let's turn it off. Will it go back to minus 60? It does. Turn it back on. It comes back without issues. Let's go all the way back to 0. Let's see if it reads the same value again. And it does. That P-semi attenuator is certainly carrying its weight. It looks good. But at this point, the ADI part never saw a large signal. So let's change that and set the attenuation now to 0 and see if the ADI part survives. Okay, similar situation, 1 megahertz. Now I'm inputting minus 10 dBm, no attenuation, so we're reading the correct value here, so that's promising. So for most of this range, it's not going to be able to read anything because we know it's going to compress, but compression is not a problem as long as it doesn't get damaged. So here's 0 dBm, and here is 10 dBm. Okay, it's obviously compressed, and here is 20 dBm, and let's push it to 25. Actually 27 to be consistent. Here's 27 dBm, is now reading minus 20. Did it die? Well, the only way to find out is to go back down to minus 10. Remarkable. It survived. Those absolute values in the table are certainly very, very conservative. I have to say, it's really quite impressive. Now, final situation, 0 dB attenuation, this time at 1 gigahertz. We're going to increase the power and see if it can survive this. So here is 0 dBm now. Okay, it's compressed already. Here's 10 dBm. Here's 20 dBm. And here's 27 dBm. Okay, let's leave it like this for a moment or two. That part is getting a lot of power now. Now let's back away to -10. Will it go back to where it used to be? It does. Remarkable. Yeah, it survives. That's really quite good. Well, might as well just push it as high as we can push it with this instrument. And here is 1 watt of power. So 30 dBm, no attenuation, straight into the circuit. Let's wait a moment here. 30 dBm is indeed a lot of power to put into something that had an absolute maximum rating of 12 dBm at its inputs. Wait a little bit. No, those numbers aren't changing. That's promising. Let's go back to -10. And it actually shifted a little bit, but not by so much. I have to say, I'm really genuinely surprised that it survives. I didn't think it would survive at all. Okay, there you go, 30 dBm. Let's leave it there for about a minute. Okay, I waited 30 seconds. Let's go back to -10 dBm. Wow, it comes back. That's really is -20. It's 1.2 dB off at the lower power, but that's okay. It's -30, 1.1 dB off. Yeah, it works. So for the power range, it somehow survives. It's obviously running non-linearly, but it survives, at least in the short test that I did. And there you have it. I hope you enjoyed this quick look at this and the internal construction and the theory of operation. I have to say I'm surprised it did survive the 30 dBm input signal with no attenuation or with attenuation. Is just a testament to how great those parts actually are, how resilient they are to operate beyond their absolute maximum range. Now keep in mind I kept those signals there for a very short time. It is possible that some combination of signals will cause it to fail, but that's going to take some searching to do. I hope you learned something and you enjoyed this. Let me know what you think in the comment section. Again, thanks to all the supporters of the channel. If you have any questions, let me know. See you next time.